Okay, so chapter this one is 12, and we're gonna get into kinematics, and we're gonna study a particle. So these are our chapter objectives, and you have it in your textbook. Okay. So mechanics is nothing but we're studying, a particle or body object, and we're going to take a look at if they're resting, if they're moving, and if they're moving, what kind of forces, are acting on these bodies so they can move. So that's all about mechanics, your force, your motion of your bodies, and if they're at rest or if they are moving, and we study them systematically. So if they're at rest, we call it statics, and if they're moving, we call it dynamics. In this course, we're going to get into the second one. Okay. If you want to know what static is, again, we're studying the body at rest, equilibrium. We call it because nothing in the world, is totally at absolute resting state, and we call it the bodies are in equilibrium with all other bodies in the space. And another part of the static, though, which is really interesting, even though we loosely call static is resting stuff and then dynamic is the moving stuff, with static, we also study the moving stuff, but it's got to be a particular way of moving, and that movement is the bodies are moving in constant velocity. So if we think about a particle, we think about a particle moving in a constant velocity. That kind of motion is also studying in statics. So in static, we think about and we think about the equilibrium, and we study the equilibrium. In static, we study the particle or object or a body that moves with a constant velocity. All right. Okay, so for dynamics, we loosely define dynamics that, objects, bodies, particles in motion. But if we gotta get down to the business, it is something that you're dealing with the accelerated motion of a body. So the body is moving, and that body has some sort of velocity, and it is accelerating. So here we're going to divide into two parts. The very first one we'll get into kinematics, and the other one is kinetics. Kinematics, we look at the geometry aspects of the motion. We'll come into it, and I believe a little bit about geometry. For kinetics, we're going to get into the analysis, right? So what are we analyzing? We're analyzing the forces causing the motion. These are just the guidelines or the ways that we do, to solve problems in dynamics. Is pretty neat here because it's listed 1, 2, 3, 4, 5, 6. So of course, every time you have a problem, you have to read very, very carefully. In science, engineering, in our field, technology, of course, in our field, we have to know what we're looking at. So when you look at something, you look at it very carefully and make sure you're conscious about what you're looking at. The same thing, when you read the problem, you have to read it very carefully and recognize every word you are reading. You got to be with the problem, not just reading whatever. Then we have to think about what's actually going on, right? The situation describing the problem. So you got to think about that physical situation describing the problem. If you need to draw it, because diagrams are really good. Awesome. You can visualize it, and it's going to help you to be able to visualize it in your mind. So you can approach the problem easier. And of course, we're dealing with the movement of motion. So when we study the motion, we usually study on a coordinate system, yeah, because we're dealing with a location, yeah, point in space. Of course, you got to use the mathematical, yeah, equations and forms and formulas, things like that. I'm going to use a necessary equation for the problem that you're solving. Okay, these are, they are pretty yes, a normal standard procedure how to solve the problem. So, and then solve it, and then you review the problem. Yeah, I mean, like, you check again if you did the problem correctly. Okay, so right here in chapter 12, we're going to study the linear kinematics. Yeah, so that's in other words, it's just, we call it very loosely, continuous motion. So we're going to study the motion, and we're not gonna study like big objects or, yeah, bodies or, you know, all other stuff. We're just gonna go all the way to a very simple particle. Yeah, so we'll study the motion of a particle, and that particle is, of course, it is moving along a straight line. Okay, so that's the situation we will be studying in this chapter. So we're gonna study the motion of a particle that moves along a straight line. Sometimes we call, all right, this a path, yeah, the path the particle travels, and you're gonna see it quite often in the book. Okay, so particle, when you think about the particle, your physics review, it has a mass. Yeah, every particle has a mass. Doesn't matter how small the particle is. Yeah, if you think about electron or proton or neutron, they still have a very little tiny mass, right? And here, when we study, right, linear kinematics, we're going to neglect its size. We just assume it's really small, okay? And of course, we don't care about the shape either, just a particle, yeah? And the type of motion we're going to get into is a mass center motion. So mass center motion here, let's say, assume, you know, like this is our particle, and then there's a center of that particle, right? And we don't care about the size, we don't care about the shape at all, meaning that size and shape can be anything, okay? So a lot of the student, yeah, let me click on this. So a lot of the student think, like, when we say a particle, they always imagine a little electron or something like that. Okay, no, this, it said so, neglect its size and shape, yeah, and we care only about the mass center motion. Okay, the mass center motion, your motion is going along a straight line, and it is a mass centered motion, and that's how we study the linear kinematics. Okay, so like I said, we just, yeah, read the problem solving, yeah, slide, and you got to read. When you read it, you have to understand and be able to relate what's really is, you know, like going on in this description. So neglects its size and shape. It said it so. We only care about the mass. We only care about it's going on a straight line, and we only care about this type of motion, which is the mass-centered motion. Okay, and so this can be a big, huge, giant rocket with different kinds of shape, as long as we are studying it on a straight path or line, and it's got to be a mass center motion. Okay, so you got it. It can also be as little as a really, you know, tiny piece of particle that you can't see, you know, like your favorite electron. Okay, I don't know why. As soon as you draw a little circle like that, and everybody thinking that's an electron or something like that, yeah, for particle. So get rid of that. Okay, so we can study, of course, position, velocity, acceleration, in kinematics. So that's all about it. Okay, so in a straight line, mass center motion, it has a mass. Don't care about the size and shape, and we're going to get into its position, its velocity, and its acceleration. And these are all telling you how it moves. Yeah. And again, let me go back to 2 slides right here. And don't forget, okay, don't forget about the geometric aspects, right, of the motion, okay? And don't forget, this one is really important, accelerated motion of the body. Okay, we deals with it. This is the reason why we gotta go all the way to positional velocity and acceleration, yeah, when we study kinematics. Okay, now a recap. So we're gonna study, we can study rockets, cars, right, projectiles, and of course as particles, yeah, because we don't care about size, we don't care about shape. All we care about are mass, center of motion right there, yeah. Okay, the very first one we're gonna get into position, yeah. Position is location, or in other words, it's just a point in space. If we study it mathematically, we usually bring something called coordinate axis in order for us to be able to study the location. Otherwise, how are you going to study the location? You can't, yeah. So that's kind of like a measurement, yeah. Measurement instrument is our coordinate axis, and we call that S, okay. And we use this little symbol S. So every time you see S, you're dealing with position, yeah. Position meaning location. Again, don't forget it's on a straight line, yeah? So everything you deal with the coordinate represent, again, location or point in space. And again, don't forget we're studying on a straight line path. Since you're dealing with the location of a particle here, yeah, here this represents a particle, so I put a label right here for you. This one is a coordinate, yeah, your system, a part of it. So if you go from 0 all the way to the positive direction, that's positive. Or you could say right, yeah, going to the right. And if you go to the left, and that's your negative direction, yeah. And I'll put it a little negative sign, of course, moving away from the origin to the left, yeah. So right now, just showing you going to the positive direction to the right, away from where? From this little origin. Yeah, origin is nothing but 0, 0, yeah, in coordinate system. If we deal with the points, so we can be able to describe or name this location. So this point is 0, yeah. Since we're now dealing with only one axis, yeah, that is the s-axis. So therefore, this point is just 0, okay. So this is your 0, and keep going to the right side, okay. As you go to the right side, you are gaining what? You're gaining a different location right here, okay. You're gaining different, you're moving different position right here, yeah, position. Oh, now at this moment, yeah, at this time, this particle is right here, yeah. So when you look at it, this particle is that distance, all right, away from this origin. And of course, in other words, we call it magnitude, all right, or S. Here we use a symbol, yeah. So that's your distance, okay. That is your distance, S. We measure the magnitude of S, and our reference point is going to be here, all right, and that's your origin, the starting point. You can say it. Your final position is right here, yeah. It is this distance, all right, this much of distance away from that origin, okay. And we call that magnitude, and it's a scalar quantity. We don't care about the direction yet, of course, yeah. If you just concentrate from here to here, the pure distance, the magnitude of distance, that's a scalar. If we think about where is it going, where is this particle going that way or this way, you have only two directions, either going to the right or left, okay. So if you go to the right, then we're dealing with a direction factor right there, so therefore we call it a vector, yeah. So the vector form, bold it, or you can put a little arrow on it. Scalar, nothing, yeah, it's just a S, okay. A regular, yeah, a regular font S, yeah, and then there is no vector sign on it, okay. So this is scalar form, vector form. I wrote it here for you, yeah. Units, since this is distant, we can use two different types of unit system. If we go with a meter, yeah, centimeter, millimeter, that's your metric. If we go with a feet, yeah, and that is going to be your British, yeah, system. Okay, now next thing that you have to know, all right, is when this little particle changes, all right, position. Okay, so now let's just think about this time interval from here to here. Okay, we don't care about the first move. So we're just going to take a look at this particle move from position 1. Yeah, I call it point 1, and that's your initial position. And the second and final position is position 2. Only here, yeah. So the first position distance, distance is always measured from the origin. Okay, so the first position distance is s, the second position distance is s prime. So if you look at, all right, there's a little prime sign right at the end of your symbol in kinematics. That means that that's the second position. Okay, mean like the second move. I'm just going to call it a second move, second thing that happened after the first. So this is now we are studying position, so this is your first position. Now prime, we're studying position, so this is your second position. This symbol can be we're going to study 3 things. So first is a position, second velocity, the same thing, velocity, initial velocity, final velocity. If we're going to use a velocity symbol, and I'm going to show you what the velocity symbol is later. Right now, just learn the no prime, that's initial, point 1. There's a prime here, that's the final, okay, point 2. Now we're dealing with position, so initial position and then final position. Okay, so now what's the difference? The difference is here, so this guy is actually it is at a location further than that guy from the origin. Okay, so this guy is nearer to the origin, so therefore they are this gap far away from each other. So what is that gap? And that's, we call it change in position. Okay, so change in position. So this little delta sign right there, okay, little triangle like thing right there is your symbol, and that means change. Okay, so in physics, okay, we call that a displacement. Mechanics, we use the same as physics, so displacement. Okay, so if you say a delta S, we're talking about displacement, right? How much of the distance your particle has been displaced from point 1 to point 2. Okay, delta S mathematically here, okay, longer distance minus shorter distance. Okay, second position distance minus the first position distance. Okay, got it? All right. Displacement is also a vector. If we concentrate only this distance, that's a scalar. But if we think about, right, your positive and negative going right or left on this line, on this straight line, then that's a vector. Okay, so vector, again, we bold it, or we put a little vector arrow sign on top of it. Okay, so delta S or delta S, so that's a vector, delta S. Okay, so displacement. So displacement, vector displacement. Okay, here scalar displacement, no arrow on top of it. It isn't bold. Okay. And I'm going to introduce another thing, and that's your distance traveled. Okay, actually I forgot, actually it's T. Okay, we usually use this symbol. Okay, let me find, where is this thing? Here. Okay, so we usually use this little symbol to define distance travel. That's the total length, okay, total length of the path the particle travel. Okay, and I'm going to show you later in a future slide. Okay, so just wait for that right now. Okay, so that's all about displacement. Okay, so here I give you some video right here, to see the change in position. So let's take a look at it. You have this, all right, in your book. Your initial position and then your final position. Okay, now we are, look at this. This is your change. Change in your distance, and we call that displacement. going to the positive direction. Okay. Okay, I think you got it. Now coming back to the negative direction. See, the displacement is decreasing. Yeah. Okay. All right. Now the next one is the change in position. All right, that's your displacement and your distance travel. Okay, so you got to know what's the distance travel is. We call it, that's a total path. So let's take a look at it going to the positive direction. See the path? Yeah, ST is your path. So right now we're going to the positive direction. Yeah. The second one, going to the negative direction, your displacement is decreasing. Your total distance is your ST down there. Okay. And when you take a look at it, you're gonna have a little bit of issue. Okay, let me redo it again to understand the total path of it, because your brain is going to question what this path is like in different direction, because the displacement is going a positive direction, and then my ST, the total path, is going like this way and then that way, because the path doesn't matter how long the path is. If you go from point 1 to, so let me draw that for you here. Where's my drawing to? So here is your point 1, and then here is your point 2. Okay, let's say we're going motion in a straight line right there. Displacement we only care about from here to here. You can take any kind of path. You can go ding, 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 and then go all the way and then come back here, but your displacement doesn't change. Okay, it's always from one point to another. Yes. Your path can also be like this, ding, 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 and then go here, who cares, So your ST is this guy, So here I have a one ST path, which is your distant travel, and this can also be ST here, another route here, but we don't care how you go, okay? We don't care which route you took. Your displacement doesn't really change from here to here, So if you think about life, and we study the life in a straight line, we assume, okay, my life is a particle because I am a human, right? And we just take a look at human as a particle, because it doesn't really matter. And let's imagine, you living your life as on a straight line. Okay, so you started at the origin, from one single cell, and then grow into a big body, and then you died, where's your location? It's right at that same original point right there. Okay, so we can draw it. It's kind of like a little example that we always use. So you're born at point 0, with one cell coming out from actually nothing, and then you live your life, ding, 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 go whatever, up and down, and then you die. The displacement of your life, studying in a linear path, is completely nothing. It's kind of weird, but things like that. So we can study many different kinds of stuff. So let me replay the second one for you, so you can see that. See that as well. I'm gonna play the second one on YouTube, okay? So that way you can see a little bit bigger. See the path? This is like going, and this one, see the displacement going to the negative direction in this case, okay? You can be able to see the path is sometimes, most of the time it's longer. So that's about your distance travel, the total length of the path. We call it the path, actually the length, the total length of the path. Make sure you understand that. Alright, then we will get into velocity. Alright. Oh, I forget about your unit, okay? For the unit for your location. So let's go back and let's just put the unit back in here for you. Okay, my bad. So in matrix is we can go with meter, yeah, centimeter. I think I put it there for you, yeah. So one moment. Oh yeah, I put it right here for you. Yes. Okay. All right. Good. So let's go into velocity. Okay, velocity is we're not gonna study, your displacement, and we're gonna bring the time into our study, because we can't really measure the velocity without the time. And you have a time, so we have space, yeah, and we have stuff in the space, and we've got the advance of these stuff in the space, and we study time between two reference points. Okay, so if you think about the time, you're gonna have a one reference point and then two reference point, and you have space, okay, and you have stuff in the space. It can be human, it can be car, it can be anything, yeah, that we know. It can be stuff in the universe, yeah, it doesn't really matter. So from reference point one to reference point two, the events are going on, yeah, from here to here. And these events are not the same. Okay, what event happened in this from here to here, the first reference point, second, third. So right now we're gonna chunk it out, from reference point 1 to 2, 3, 4, reference point 5. Okay, and if you look at the stuff, they're not the same. Okay, some events happen here, and some other events happen here, some other events happen here, and then some other events happen here. Like you were, 1 hour ago at somewhere, I don't know, yeah, and now you're in class. Okay, like that. So, and the events, right, the series of events that we study, and we call that, right, that interval time. Okay, so the clock and stuff like that, right, digital clock, manual clock, is showing you this little unit like 12, and then we have 12 hours. We put that in, and that's just a measurement device. Okay, measurement device, or what's going on, the events, yeah, from, okay, let's just start it from 12, yeah, all the way to, let's say, 6. Okay, what happened from 12 to 6, and we measure it. Oh, from 12 to 6, yeah, I was asleep, and then like it's 1 o'clock, I was asleep, then 6 a.m. I got up, yeah. Kind of like that. So that's clock is just a measurement device, yeah, measuring, yeah, at this reference point, at this reference. So these little units on your clock is your reference point. Okay, so here we'll take a look at it. So now we have a two reference point right here, and we call that location. Of course, that's your first location, second location. From this reference point to that reference point, if we measure with a clock, or digital clock, or time it, we get this, right? Delta t, the change in time from here to here, and we call that a little time interval. In this time interval, all right, the event, because right now we're studying only one single step, which is your particle, right, on a straight line. So at that time, what happened? This particle moved from here, first location, to the second location. Okay, that happened, a single event, a single time interval. A motion has happened on a straight line. Okay, particle changes position 1, from position 1 to 2. Okay, and here your displacement is from here to here. Who cares what is your total distance traveled is, yeah. Okay, so now we're gonna deal with this two, displacement and a time interval. This displacement happened over this time interval. Okay, so this displacement happened in that time interval, and mathematically we write it in ratio. So delta S, okay, is to delta T, because we're studying the first thing in relationship with the second thing. All right, this is your space, event in the space. Your particle move from here to here, event in the space. all right, and that's your time. They're related to each other, okay? So this is your relation. So delta S is to delta T. Mathematically, we write it in this form. So delta S divided by delta T, okay? Delta S by delta T, all right, your math, yeah? So that's, we call it, that's the average velocity, all right? The rate at which this particle moves. It takes, all right, it moves this much of displacement or distance over that time, okay? So that's, we call it average velocity. Average velocity is nothing but the rate a particle moves, all right, over a time, okay? So that's your average velocity. Now we're going to study, what if the time is too small, going towards a zero? So smaller the smaller, smaller the smaller the time. We got to take, right, instantaneous velocity, something that happened at an instant. So let me get rid of this drawing stuff. Okay. So instantaneous velocity, we have to take the limit because your time is approaching to zero, meaning like it's reducing. Okay, it becomes smaller and smaller, very instantaneous. At that time, we're going to use, all right, delta S limit, delta T approaching zero, delta S divided by delta T, so delta S by delta T. And we got an equation, okay? So that equation is velocity, all right, delta S divided by delta T, meaning like very little tiny change in displacement over very little tiny change, that's little d is your delta, okay, in time, okay? So it's a very instantaneous velocity, okay? The rate can be really, really fast or really slow, depending on which direction you're going. Average is kind of like laid back, you keep going with the same velocity. And then something came in, let's say you're driving a car, we're going to assume the car is a particle in a straight line on the road, and all of a sudden, something happened and your velocity changed because you went over, you went over a hole on the road or something. No, your velocity changes instantly. It changes, And what happened? This much of velocity changes at that time when you are, let's say, like going over a rock, a big rock or something, Okay, let's recall our mathematical relation. So I said that delta S is to delta T, okay, meaning like you can, all right, move, of course, your delta S, all right, this guy to the other side of the equation. This is your equation. So you can move this thing to that side, okay? So if you move that thing to that side, you have V delta T, okay, equal to delta S. So you have V, writing is pretty bad, and then delta T, of course, and then your delta S. So at that time, you can clearly see delta T and delta S, they are directly proportional to each other. We call you call, okay, delta T is directly proportional to delta S. Okay, now we're just writing it reversely. So what it means, okay, if magnitude of delta S increases, your delta T is going to increase. Okay. And if it decreases, your delta T is also going to decrease, okay? So that's a directly proportional to each other relationship, okay? This is just reiterating, okay, here. So delta T approaches zero, then your instantaneous velocity, okay, is this time is going to be very, very small, meaning like it could be at zero. It happened very abruptly. So your delta T won't be this big, okay? It's going to be like very, very small, Okay, so let's take a look at velocity going to the positive direction. So you can see how your displacement changes, and that's happening over time, and you have velocity, okay, your average velocity, let's see the negative direction going. The same thing, your delta S changes and you have your velocity happening at that time. Okay. Okay, then we'll get into speed. Speed is nothing but we're just studying, okay, the magnitude of velocity. All right. Just like the position here, position is the magnitude of your displacement. The speed is the magnitude of your velocity. So if we think about the average speed, and that's a positive scalar quantity. So speed, again, your magnitude, okay, of your velocity, and your average speed is your scalar quantity, okay. So if we want to define just a total distance traveled, yeah, remember your ST, this guy, yeah, total distance traveled by particle divided by the change in time. So here, okay, so for velocity, we're dealing with the direction, so you've got right here a displacement, okay. For speed, okay, see like how this is bold, or you can put a little arrow here, no bold, okay. We're dealing with the distance traveled, okay, over a period of time or change in time, okay. So that's a change in time. So here's our diagram. Yeah, your point 1 is going to be here. Your point 2 going to the negative direction. Yeah, here is your negative, your positive direction. This is your distance travel. Your distance travel total path. Okay, go go all the way to this position. Okay, yeah. So that's your ST, your total distance traveled by this particle. Yeah. Your second position is here. Your displacement. We don't care about the path. We just go from this point to that point on a straight line, bang, and that's your delta S, your displacement. Yeah. So if you study the displacement, we get average velocity. If we study the distance traveled, right, distance traveled, we're gonna get the average speed. So for this particular problem, we are heading to the left, yeah, so therefore your velocity is negative, yeah, so that's where, see, average velocity negative, your displacement divided by your time interval, right here your average speed, distance, yeah, travel divided by your time interval. So velocity again is your vector, yeah, vector, therefore we're gonna account for the direction, yeah, your particle is going, in this case going to the left. All right, the next one is acceleration. Yeah, acceleration. We usually use A. Oh, did I mention about the velocity unit? I forget. So let me go back. Oh, here, yeah. So velocity. Okay, since we are dealing with the displacement over time, we use a meter. Yeah, meter per second. Second is your time. A unit or British system is going to be feet per second. Let's go back to our acceleration. Acceleration, we use A, okay? We call it, look at this is particle, yeah? Particle is quickening or speeding up, yeah? Speed is increasing, okay? So what are we doing? We're studying change in velocity this time over again, a time interval, yeah? So when you look at it, we have the initial velocity here. It is initial because there's no little prime sign right there. And then the final velocity here, yeah? So velocity changes from here to here. From this point to that point, the velocity change, and that is your change in velocity, delta V, yeah? It happened from here to here in that time interval, okay? So average acceleration is delta V divided by delta T, okay? Change, we can get it just like we did, yeah, for our displacement. So delta V is equal to V prime, yeah, V prime, the second one, minus the first one, which is your initial velocity, V, okay? This is just showing you we're going to the positive direction, yeah? Okay, if we take the limit, meaning like if we take the instantaneous velocity, yeah, your time is really, really, really tiny change. So this little d means like we're studying the very tiny changes, yeah, of times going smaller and smaller and smaller and smaller, approaching zero. At that time, we got again the acceleration at an instant, and we call that instantaneous acceleration. Delta v, yeah, divided by little d. T is a delta t. That's a big delta in symbol, yeah. When we study a little time, then we go little d, yeah, v by dt. Of course, we're going to the positive direction. It's showing like that. That's going to the positive direction, yeah. Okay, how do we get this? Yeah, so if you think about it, you have an average, yes, acceleration is dv divided by dt. So what we did is here, this v, all right, is a velocity, so therefore we can be able to put our little delta s, yeah, divided by delta t. So we're putting the equation, yeah, substitute the equation, the velocity equation into this equation, okay? So average acceleration is delta v divided by delta t. V is delta s by delta t, okay? And we're gonna solve it. So first, you're gonna leave that because it is, yeah, above the bar, okay? And then we're gonna put this down because that's below the bar, yeah, which is your divider bar we're talking about here. And then you have d and d, and that's a d square, yeah. And then this is your s, yeah. That's your displacement, of course, change in displacement, yeah. And then right here we have d, t, and the dt. You have a common d, so we're gonna take that out. So you have t squared, yeah. So that's how we get d squared s divided by dt squared, okay. I forgot that's right there. Okay, so your instantaneous acceleration, yeah, we can be able to write it this way or this way, yeah, d squared s divided by dt squared. We can also go straight in dv divided by dt. This is, we're defining this using the displacement, okay, position. So here we're defining the acceleration using the velocity, okay, but it's the same thing. And here, if we study little time, yeah, instantaneous, yeah, velocity ds divided by dt, and this is the one we're putting right here, yeah, because this is a dv anyway. So that's how we do it, okay. Your unit is going to be acceleration, since your time is square here, yeah. So you have meter per second square. British system is going to be feet per second square, yeah. Okay, then we'll get into another, yeah, acceleration. Let's wrap it up. So if you take a look at it, okay, this is just showing you that you can be able to, okay, put this little v to that side, yeah, mathematics dealing with your equation. So we can move around, yeah, all the factors, and that's so we put the v to that side. So we get v dv. We're gonna put the a to this side, so we get a ds. Okay, it's just another way of writing dt. Okay, your dt, don't forget it. It comes from the little change in d, yeah, which is on this guy. So that's something that we can also write, okay. Equation is acceleration times delta s is equal to velocity times delta v, yeah, because your dt is ds by v. If you wanted, I can, yeah, put this one here for you so you can be able to see this, okay. See, your v is ds by dt, and we put this dt to that side and bring that v to this side, so you get, yeah, the same equation. We're just changing the side, okay, and the factors. And the second equation, yeah, come from here. And your second equation is your instantaneous, yeah, acceleration, which is this little guy. See that? So we're putting this on this side and dt to that side. Yeah. I hope you can see it. Well, I can, yeah. I gotta go to school and code it like this, okay? And you see, so we're just switching the position here, yeah? So we put this on that side, so you get dt. We put that on this side, so you get this, yeah? The same thing here, we put this here, so you get this. We put the dt on that side, so you get that, yeah? And of course, since dt is a common thing, this modified equation, they equal to each other. So again, we put this 2 here, yeah? We put a to that side, and then we put b to that side, so you get this, okay? Make sure you play with this when you study. Alright, the next thing you have to know is when a particle is slowing down on a straight line, yeah, and we call that the speed is decreasing. So when you study here, your first, yeah, your acceleration is going that way because you are slowing down, okay? So your first, of course, this v is your velocity, initial velocity, and then your final velocity, yeah, change in velocity. We subtract the initial from the final. And our direction is, yeah, acceleration direction is minus, meaning we are decelerating. Your position, of course, you're going from here to the positive direction. Your displacement is positive, but your acceleration is negative because it is slowing down. The particle is slowing down. Okay, be careful around here. And we call that, of course, negative acceleration. So if we think about a particle initially at rest, right, let's say at the origin, and then a moment later it is moving with a velocity, yeah, and that velocity is this much, then you can have an acceleration, yeah, as long as there's a change in velocity, you have acceleration. So the starting point, there's no velocity, yeah, so your v is 0, your position is 0, but after a moment later, your final velocity, okay, is you get a final some sort of velocity right there, so you have some sort of acceleration at that time, okay? But if we think that velocity, that v is constant, okay, if that v is constant, then acceleration is 0, yeah, completely 0. Here it's just showing you there's no change in velocity, okay? I shouldn't write this, you know, so this is probably I copy it wrong, yeah, sorry. So when the v is constant, okay, here is just showing you your change in velocity is 0, all right? There's no change in velocity at all because you're traveling with a constant velocity, okay, starting with the one velocity and keep going with the same velocity, okay? So at that time, you can get the average velocity, the same thing, delta v divided by delta t. We put there's no change in velocity, so 0 happening in that time interval, delta t. So you get average velocity. There is no average velocity, okay, completely 0. If the particle is traveling with a constant velocity from an origin, okay, or anywhere, but even if we in this example we say, okay, let's just, you know, think about like it started from a rest or started with a constant velocity, yeah. And then we'll get into constant acceleration. We put the little c, yeah, subscript c next to your acceleration symbol, and that means we're traveling with a constant acceleration. So when the acceleration is constant, right, we can be able to study the kinematics, yeah, by integrating it. And we're going to use our 3 equations, yeah, your acceleration, your velocity, and then your acceleration modified equation, okay, all of them we can integrate it and then related to constant acceleration velocity. Again, this is your position and time. Okay, so let's take a look at one by one. Okay, so since some of you you haven't done integration, so don't worry too much about it. Okay, we can go with the regular equation. However, you need to know that we integrate it in order for us to be able to study the velocity at a function of time. Yeah, because you have changes going on. Yeah, v0 to v and then time again. We have change, and integration is nothing but we're just studying something, in changes. Okay, we're studying the changes. It's a way of mathematics way that we write it in this, okay, in equation. But the meaning is we're studying the changes. Yeah. Of course, a very minute changes. See this little d, okay? Don't forget these are very tiny little changes. So constant acceleration, we're studying the tiny little changes of velocity over time, yeah? Our assumption is your velocity is equal to v0, all right, initial velocity, and your time is 0, yeah? So this means like at the time at time at 0, okay, we are assuming, okay, your v is v0, okay, at time 0, okay, and we're gonna go to the positive direction. So at that time we get v, your constant acceleration is right there we use. Yeah, it's got to be the acceleration completely constant. That's what we're talking about in this equation. Sometimes we call this, equations of the equation with constant acceleration. So v equal to v0 plus a t. Okay. So one of the example is you're gonna release your ball from your hand, yeah, all the way down, yeah, to the ground, and it has a 0 velocity, but your acceleration is your g, yeah. So that's your 9.81, your gravity. And that acceleration is constant, okay? Okay, the next constant acceleration is we are going to study the position at a function of time. Yeah, the same thing, studying the position at a function of time. When we say that, we're just studying, okay, taking integration, okay, for little minute changes of position, but we're studying in a little minute changes of time, right? So we're going to integrate this, okay, and our assumption is at time, all right, as t equal to 0, the same thing as is equal to at 0. That's your initial position. Another constant acceleration equation, and now here we are dealing with the position, okay, so at 0 plus v0t plus 1 by 2 act squared. Yeah, you gotta get these equation. And the next one, and we're going to study the velocity, little tiny changes of velocity at a function of the little tiny changes of position. Okay, assumption s is equal to s0, v is equal to v0. It doesn't, your equation is not true if you don't have this assumption. Okay, so we got to strictly follow these condition every time you want to use this equation to solve. Try to calculate, like the magnitude of a velocity. You have to meet these assumptions. Okay, otherwise you can use this equation to solve the problem. Yeah. So make sure you understand that. So this is another equation with constant acceleration. This is not just whatever acceleration, it is a constant acceleration. So when you read your problem, you're going to read very carefully, am I dealing with the constant acceleration or am I dealing with just a regular acceleration, okay? Okay, these are just important points and I want you to read it by yourself, okay, covering everything that you need to know. These are just for the procedures for your analysis, okay? So when you do your review, make sure you hit these 3 slides. Alright, so that's all about position, acceleration, okay, and your velocity, okay. Make sure you get that before next class. Yeah, that's it for today.